Hi everyone, I'm Kent, and this summer I've been working with Professor Matthew Reed and Wei Zhou on a project called Handling Flexible Parts, and today I'll be talking about the force and moment exertion part of my project. So, a little bit of an intro here. As we know, all manufacturing industries have a lot of employees that assembles products, and they also have a lot of flexible parts such as cables and harnesses that have to be assembled every day. So these workers are the ones who interact with all the flexible parts. Now, the big question behind this project is how the workers and the flexible parts interact with each other. Do the workers have to exert some kind of force in some direction, or is there any moment caused by the posture of how the workers were assembling these parts? These are the kind of questions we want answers to, and by doing this research, I found some of the answers to those questions. So, we set up an experiment with 6 subjects consisting of 3 males and 3 females, and the subjects were instructed to grasp and manipulate 4 categories of flexible parts: wiring harness, cable, hose, and electrical connector. Firstly, these setups were presented to the subjects, and they were told to attach each of the flexible part to a flange, a pin, or a female connector block. Force and moment data were later measured using equipments I will describe in the next slide. Some equipments that were used in this experiment were, firstly, cyber gloves, which were used to track the positions of the subject's hand. Secondly, a motion tracking system, which were used to track the positions of the subject's other body parts, such as head and shoulders and elbows. And lastly, load cells at part endpoints, which were used to quantify the moment and forces exerted by the subject. So we did several different test conditions for each flexible part. For the cables, we had them positioned at 0 and 90-degree orientation. That means the cables were twisted 90 degrees so that the person had to twist it back 90 degrees in order to attach it. For harnesses, we had 2 different sizes of harnesses, small and large, and we had each of them positioned in 3 different orientations, 0, 90, and 180 degrees. For hoses, we also had 2 different sizes of hoses, small and large, and we had each of them positioned in 3 different offsets: a 0 offset, 5 cm vertical offset below the target, and 5 cm horizontal offset left to the target. And for wiring connectors, we had it positioned in 2 different horizontal offsets, 5 centimeters to the left and 5 centimeters to the right. Some objectives of current analysis are to quantify direction and magnitude of forces and moments exerted during the interaction, and simulate interactions between workers and flexible parts. After the experiment has been done, the load cell data were extracted and calibrations were applied. Also, I had to visually verify the data traces and identify any anomalies that might be on the data. Unfortunately, in the experiment, several moment channels were lost due to electrical connection issues. So, I will show you some sample data plots from the experiment. And for each of the flexible parts, I have a consistent coordinate system set up as shown in the slide. If you are standing in the position of the subject, positive X is to your forward, positive Y is to your left, and positive Z is always pointing up. So the 2 graphs are the 2 different conditions of the cable trials. The left one is the 0-degree orientation trial, and the right one is the 90-degree orientation trial. For each of the cable trials, the subjects can mostly exert moment in the forward direction, in which this case is the positive Y direction. There might be some pushing downwards towards the insertion, but that wasn't too significant in this case. Some observations that were made from the cable trials were that the orientation doesn't affect the amount of lifting, in other words, the Z-force. I found an average of 8.6 newtons and 10.61 newtons on the 0-degree orientation, and an average of 6.62 newtons and 12.16 newtons on a 90-degree orientation. Also, hands generate a relatively small magnitude of force compared to other flexible parts that needs over 200 newtons to perform the task. I found an average of 37.77 newtons and 64.68 newtons for 0 and 90-degree orientation respectively. These are some sample plots from the connector trials, the left one being the 5 cm offset to the left trial, which I will refer to as the negative 5 cm trial as from now on, and the right one is the 5 cm offset to the right trial, which I will refer to as the positive 5 trial as from now on. And what's going on here in the graphs is that there is mostly a forward pushing force going on by the subjects in both test conditions. And in the negative 5 cm trials, there were some downwards pushing force, and in the positive 5 cm trials, there were some horizontal pulling motion to the left with respect to the subject. Some observations that were made from the connector trials were that both trials need roughly the same magnitude of force to perform. I found an average of 104.62 newtons and 111.57 newtons for negative 5 and positive 5 trials respectively. The oscillatory pattern is a one peak during the insertion of the connector, followed by a constant push later on. Also, the negative 5 cm offset trials have a pattern of some downwards push, and the positive 5 cm offset trials have a pattern of some horizontal pull. And the horizontal pulling on the 5 cm trials has an average of 28 newtons, while the vertical push downwards on the negative 5 cm trials has an average of negative 34 newtons. These are some sample plots from the small hose trials. The left one is the 0 offset trial, and the right one is the 5 cm vertical offset trial. In these trials, we can see that mostly there is only a forward pushing force in both test conditions. This one is the 5 cm horizontal offset trial. In these trials, we also see the forward pushing force we saw in the two previous conditions. But here we also have some pulling force to the right of the subject. Now these are some sample plots from the large hose trials. The left one is from the 0 offset trial, the right one is from the 5 cm vertical offset trial, and this one is from the 5 cm horizontal offset trial. Basically, we have the same things going on as in the small hose trials, but we have bigger magnitude of forces exerted, and we also have more oscillating moments exerted because the large hoses were relatively harder to insert to the target compared to the small hoses. So, some observations that were made from the hoses trial were that large hoses need bigger force exertion in the insertion direction, and forces of small and large hose differ by 55, 52, and 43 newtons for 0 vertical and horizontal offset trials respectively. Every subject has a different insertion pattern depending on their posture. Also, trend of force exertion is to oscillate with gradual increase. Some other findings were that the horizontal pulling force exertion on the horizontal offset trials needs an average of 50 newtons for the small hose and 63 newtons for the large hose. The magnitude of force exerted by hand is largest on the horizontal offset trials. Vertical offset and 0 offset trials need relatively same amount of force to perform, as I'll explain in a minute. So for the small hose, the horizontal trial needed 162.6 newtons, which is bigger than 151.45 and 152.67 newtons, which doesn't really differ that much, that were exerted in the vertical and 0 offset trials. And same thing for the large hose. The horizontal trials needed 270 newtons, which is bigger than the 242 and 239.59 newtons that were exerted in the vertical and zero offset trials, in which you can also see that the number doesn't really differ that much once again. Despite all those findings, this research project is still far from being complete. So the next steps to be done in this research project are to do moment analyses for all the flexible parts and to develop a concise statistical representation of task and object effects on hand force patterns. Lastly, I want to thank Professor Reed and Wei for all the learning opportunities this summer. It's been an awesome summer. And I also want to thank you guys for listening. See you next time. Bye-bye.